Hello, everyone. Thank you for your attention to my presentation. My presentation will provide an overview of how nano-sized uh, nano-sized or micro-sized particles can affect hydrogen trapping or hydrogen embrittlement in aluminum-based structure. Studies like this can offer new insights because the effect of these particles on hydrogen trapping or hydrogen embrittlement is still unknown. Some studies indicated that these particles can mitigate hydrogen embrittlement, while the other studies suggested that these particles can exacerbate hydrogen embrittlement, even for materials with similar chemical composition. In a part of my research work, through a series of research studies, we could identify which characteristics of these particles can affect their property against hydrogen. In one of our studies, we investigated the effect of dispersoid particles, common dispersoid particles, Al3ZR and E phase on hydrogen embrittlement in 7,000 series of aluminum alloys. For this purpose, we prepared two alloys with similar zinc, magnesium, or copper content. One alloy contained chromium, while the other alloy contained zirconium. From SEM, TEM, and HRTEM results, we understood that microstructure of these alloys, there is no differences in the microstructure of these alloys, while the nanostructures differ. This is because in one alloy, we had chromium-containing particles, with incoherent interface. You can see here these dislocations in the interfaces. While in another specimen, we had coherent zirconium-containing particles. The SSRT results showed that the specimen which contained chromium alloy with incoherent particles was sensitive to hydrogen embrittlement, while the other alloy was not. As you can see here, in the fracture surface of this specimen, which was sensitive to hydrogen embrittlement, we observed indications of intergranular fracture mode, while in other specimens, we didn't see any evidence of brittle fracture. The TM results after deformation showed that the interaction between dislocations and chromium-containing particles leads to the formation of dislocation loops and a higher density of dislocations. However, in zirconium-containing particles, dislocations can cut particles. Therefore, we have a lower dislocation density. The result of TVS showed a significant hydrogen trapping at grain boundaries and dislocations in the specimen which contain incoherent particles. Also, as you can see here, hydrogen micropooling technique showed the accumulation of hydrogen in the grain boundaries of these specimens. While in another specimen which contained coherent particles, we observed a good distribution of silver particles in the microstructure, and also we observe an additional peak in the TDS result of this specimen. This coincides with a reduced hydrogen trap at dislocations and grain boundary in this specimen. From these results, we concluded that when we have coherent particles, coherent Al3ZR particles inside the material, these particles can act as strong hydrogen traps and prevent the grain boundaries from reaching the critical hydrogen content required for crack initiation. Therefore, they can suppress hydrogen embrittlement in 7,000 series of aluminum alloys. In another study, we investigated the effect of size of these particles on hydrogen embrittlement or hydrogen trapping in 7,000 series of aluminum alloys. As you can see here, for this study, we prepared 4 alloys. 2 alloys contain coherent Al3ZR particles with different sizes, fine and coarse, and the other two alloys contain incoherent particles with similar chemical composition, Al3Zr. The result of TEM showed that after aging, we had similar nanostructure in these specimens. The result of SSRT showed that only one of the specimens which contained coarse coherent particles was hydrogen resistant. The fracture surface of the specimen showed that specimens which contain incoherent particles showed intergranular fracture mode. However, in the specimen containing fine coherent particles, we observed transgranular fracture mode and crack initiation at the interface of these particles. DFT calculation and TDS results and in situ SKPFM results showed that the coherent particles can act as strong trap sites. And the size of them is not important. From our results, we concluded that when we have incoherent particles inside the materials, they cannot trap hydrogen. Therefore, grain boundaries can reach the critical hydrogen content for crack initiation, and we have hydrogen embrittlement. When we have coherent particles, they can trap hydrogen. However, when they are fine, they can be saturated soon, and crack initiation occurs at their interface. In another study, we investigated the effect of nanochemistry change of strengthening precipitates in 7,000 series of aluminum alloys. In our research, we understood that additive manufacturing can provide a unique macrostructure. As you can see here, in superimposed EBSD result, we have a good distribution of soluble second phase particles inside the grains, while in commercially available alloy, we can see the segregation of these particles at grain boundaries. This unique macrostructure of additive manufacturing leads to the nanochemistry change of strengthening precipitates after solution heat treatment and aging. As you can see here, the strengthening precipitate in additively manufactured alloy contain copper. However, we don't have copper in precipitates in commercially available alloy. The DFT results indicated that copper makes this precipitate strong traps. And this is maybe one of the reasons why additively manufactured alloy had a better performance, had a better mechanical properties in presence of hydrogen comparing to other specimens. The details are in our paper. In another investigation, we investigated the effect of distance between macro-sized soluble particles in 7,000 series of aluminum alloys. For this purpose, we prepared some specimens with different densities of soluble second phase particles. The result of SSRT showed that in absence of these soluble second phase particles, and also when we have a higher density of these particles, we have hydrogen embrittlement. The fracture surface of this specimen showed that when we don't have these particles inside the material, we have intergranular fracture mode. However, in higher density of these particles, we can see transgranular fracture in the corner of the fracture surface. The HMPT results indicated that we have accumulation of hydrogen around these particles. From this result, we can conclude that when these particles are close to each other, the hydrogen-induced cracks can coalesce. And therefore, we have a premature fracture and hydrogen embrittlement in these specimens. And also, when we don't have these particles, the grain boundaries can trap more hydrogen, and we have intergranular fracture in the specimen. From my work, we can conclude that we can offer that if we want to suppress hydrogen embrittlement in 7,000 series of aluminum alloys, we should control the size of AL3ZR particles as dispersal particles, and also we should change the nanochemistry of strengthening particles, and also we should have soluble second phase particles with a certain distance between them. If you have time, I want to continue. Yes, I have time.
Sorry?
Because I want to continue if I have time.
Yes, 2 3 minutes.
Yes,
Yeah.
okay. Hydrogen trapping at coherent interfaces was also observed in another studies of ours. In this study, we prepared composite material, and we observed that during processing of composite material, aluminum carbides can be nucleated at the interface of carbon fibers and grew into the aluminum matrix. The HRTM results indicated that these particles are coherent. The TDS results, the comparison between TDS results obtained for this composite material and pure aluminum showed that we have 3 additional peaks in composite material. From the literature and in situ SKPFM and hydrogen macropyrin technique, we understood that this peak is related to the hydrogen trap, related to the hydrogen trap at coherent interfaces. And this can affect the hydrogen permeability in composite material.